We also take a look at the discipline from a very basic physics point of view. Jason Burke today, a longtime colleague of this department, will be talking about low-energy nuclear reactions, low-energy nuclear physics studies at Livermore National Lab. He was a physics technology degree at John Abbott College, an undergraduate at Concordia University in Montreal. Is undergraduate research at the NRC Canada 4 times, master's and PhD at UC Berkeley in physics, and a postdoc at staff at Lawrence Livermore from 2004 to present. And I just recently learned he's an adjunct professor at St. Mary's. I think he's well known to this department. I think many of our students here interact with him. And so take it away, Jason.
Okay. So this was really pitched at the graduate student level, like to give you an overview of the projects we have going on, see if anybody's interested in working with us, etc. Justin's already with me, Aga, Senator Tomey's starting. Right? Sasha chose a different group, but that's okay. As long as you end up at the lab at some point. All right. So we have a lot of grad students, postdocs, undergraduates, visiting scientists, etc. So I'm going to try to go over this in 50 minutes. This is going to be a little quick, but we'll try to hit all the high points, and I'm around for questions then. So motivation, I'll tell you what the problems I have to deal with at the lab, why I have to measure these things roughly. I can't tell you everything, but mostly. I'll talk about Starlighter and how we're doing surrogate reactions for N-gamma, our upgrade to Hyperion. That's for N-gamma reactions. Richard's my postdoc working on that. Neutron Stars is how we're going to measure N2N reactions with a new technique. Rob Casperson is a staff member. He was my postdoc. He's now working on this. And then Hydra, that's how we're going to measure and do studies of neutron-induced fission. We're doing this all with surrogate reactions. So instead of using neutrons, we're doing charged particle reactions to induce the reactions we care about. And then I'll just give you briefly in our external collaborators and groups we work with. So with the lab, it's Lawrence Livermore. I'm responsible for figuring out all the reactions of interest from fusion, like NIF type stuff, all the way up to reactions on the actinides and everything in between. So fusion reactions are mostly dealt with through theory and modeling at this point. We don't do a lot of low energy stuff like 10 keV, DT fusion or 100 keV cross sections like that. Capture, N2N reactions, and charged particle reactions are anywhere between the light ions, like light ions like neon and stuff, all the way up to just below the actinides. And then in the actinide region, we deal with fission, capture, and N2N as well, with neutron captures. Okay. So we have to be fairly flexible in the type of apparatus we use and the physics we need to know about and how we interact with theory and modeling groups to be able to get solid answers out of the experimental data. An example. So we need a deep understanding of cross-sections in nuclear structure to be able to interpret reaction networks. So for instance, we're interested in reactions off yttrium-89, but also in N2N, what happens on yttrium-88, and what happens, for instance, on yttrium-87, and the isomers that may be around as well. Like this guy's a 13-hour half-life, right? So these are complicated. There's N2N reaction here on yttrium to make 89 to make 88. This is the only stable one, by the way. Then you've got N2N and N-gamma reactions that occur in 88, so you can go either way, you can capture or decay. And then same thing here, mostly capture. So we've been tasked to try to do this, and you can't even make targets of these things. So how do you do it? So 89 being the only stable one, this is 106 days. So some guys at Los Alamos, at Dance in particular, have tried to make some 10-ish year half-life targets, right? But making them isotopically pure is really hard as well, and these things are extremely hot. So that's why we're going to do surrogates. But just to give you an idea, 100 micrograms of yttrium-87, this 3-day guy, would be 45 curies of activity. That's 10 to the 7 becquerel, or 10 to the 12 becquerels. Forget it. Not going to make a target out of that. 100 micrograms of the 88, which is 106 days, is 1.5 curies. Not bad, but put it in front of your gamma detectors and they're going to light up. So that's nearly impossible as well. So instead, what we do is this thing called the surrogate approach. And this started in the 60s, actually at Lano. 60s and 70s at Lano. They did some experiments up at the 88-inch back in the 60s as well. It was Chip Britt, Jerry Willoughby, and a whole host of characters there. They mostly looked at fission, and because they were using tandem accelerators, they only went to about 6 MeV or so of excitation energy. It's kind of what limited out with the accelerators they had. but they made some good progress. So based on that, about 10 years ago, I was hired as a postdoc to start working on this whole program and try to get it working. And it was tricky because everybody's learning everything for the first time again in 40 years. So what we do is we're trying to predict what the neutron cross-section is here. We know that we can form the neutron, that we can have a neutron come in and capture on the nucleus. That's the formation cross-section for neutron capture. That, fairly well known. What's not known is what happens once that neutron captures. Because over here you can have gamma decay, you can have particle emission or fission, particle emission here or fission from this compound nucleus. So the theorists don't like to take a shot at measuring what the heck happens with the branch. Okay, that's tricky. Very large uncertainties. For N gamma, we're talking factors of 2 easily. And that's where they know a lot about the nucleus that they're dealing with. So instead, what we're doing is we're measuring the probability for that branch to occur, but we're making the nucleus, the compound nucleus, the excited state nucleus, excited nucleus, not the excited state nucleus, a different way. So this is just a DP reaction, for instance. We do PD, where you do a pickup reaction with helium-3 prime, helium-3 alpha, alpha prime, etc. Each one has its strengths and weaknesses. So instead, theory predicts what the compound nucleus reaction should give you here, and that we can check against our measurement directly. And now, of course, time machine. Because that's what I've got to worry about. Right. And what we do is we measure the compound nucleus here, and in reality, we measure really just the probability that the photon or the fission or whatever happens, the neutron gets emitted, happens. So that's just the particle ingoing, like an alpha beam at 40 MeV, the outgoing scattered particle, and the gamma ray associated with that nucleus, divided by the scattered beam. So how many times did you excite that nucleus to that energy? Okay, you'll see a little bit of this as we go along. Where do we do this work? For the first 6 or 7 years, we were at Lawrence Berkeley National Lab, just up the hill, right, at the 88-inch. We needed more and more beam time as more and more people wanted to work with us. The current group is around 50-ish or 60 people, 10 or so different institutions. So we just outgrew our ability to get beam time, really. So instead, we went to Texas A&M. They had just stood up this K150 Cyclotron, which is the sister, literally the same age and time scale as the one up the hill. And it just happens to be lucky that the beam height is exactly the same. It's 4 feet off the ground. So everything kind of fit right in. So over here is our dedicated beam line. It comes out through the cyclotron, whichever beam you want, more or less. Comes through this 170-degree bend magnet. That is super helpful because that bend magnet basically splits out the turns from the cyclotron, because you can get more than one extraction turn from the cyclotron, which means you have more than one energy of beam. Mostly it's all in one, but then there's tails, wings. That comes through here, switches again, and then right down to our beam line. Now keep in mind there's this other thing called Nimrod. Did not pick the name. All I care about on that thing is the neutron ball around it. It's 4.5 tons of superconductor doped with gadolinium. We're going to see that again. This is Neutron Stars that we want to turn it into anyway. And then this is our line for doing the gamma ray measurements. So here's Richard Hughes standing there, and this is our 6 Clover detectors surrounding the beam line. The beam comes from the right, goes to the left. Behind it over here is the neutron ball. So typically what we'll do is we'll run in with a beam anywhere 28 to 30, 50 MeV, scatter off the target, detect the scattered particles. So I know the beam energy, I know the outgoing particle, I know how much energy I dumped into the nucleus, whatever it is. Okay? I collect most of the beam in the Faraday cup so I can actually measure cross-section for the theorists and know what we're doing for exciting the nucleus and how much. We know, of course, the target thickness and all that. Looking from the top, the way we detect the particles here is using a silicon telescope. So we have various silicon telescopes that are actually CD detectors. They're like about the size of CD, honestly. They have 24 rings, so we get theta, and then phi is measured with up to 8 sectors. If we fully break it out, we can have 48 rings and 16 sectors. At some point, you run out of electronics and patients to do analysis, so we pick the right combination for whichever experiment we're doing. So for yttrium, for instance, well, in general, we run about 15 experiments now. And our energy resolution is about 75 keV, that's 1 sigma. Gamma resolution for the whole array is about 1.7 keV, so that's pretty good. We cover an angle range of about 30 to 60 degrees. This is a little limited, so that's why we have another detector system coming online. So for the yttrium case, we did yttrium 89 PD, and we wanted to get all these cross sections here. Okay, so this, don't get too confused. The red lines are going to the ground state. The blue lines are going to this isomer. The green lines are going to this isomer. That means we're trying to measure N gamma to here, okay, from these two states. N gamma from these two states to here. N gamma to the ground state, okay? So we did that. It took us 13 days. We had over 20 students and postdocs and researchers from about 5 institutions involved. We ran it during the summer. They had a whole bunch of summer student, the REU students, which helped a lot. So, okay, I don't want to confuse you too much, but everybody always asks me, well, wait a second, you're measuring charged particles. How does that relate to neutron energy? Okay, so just follow the bottom line here for a second. You come in with a 28.5 MeV beam, right? You have a Q value for the reaction. This is PD. So immediately, nuclear physics says you're going to lose 9.25 MeV. So now you have a deuteron at 19 MeV, but now the nucleus has 0 excitation energy, okay? So now you've made your yttrium 88 nucleus, for instance. And as you excite that nucleus up and up and up, you have to get to 9.3 MeV, 9.35 MeV above the ground state before you can kick out that neutron. If you captured a neutron, okay, on yttrium 88, you'd end up right here to begin with, because that's what the neutron Q value is when you come in. So from here on, this is what we call the surrogate region, or the equivalent neutron energy is 0, and you move up here for about 2 MeV is what we ran into before the coolant barrier kicked in. So below here, I know that the nucleus can only decay by gamma decay back to the ground state. There's no other channel open, okay, proton emission rate otherwise. And above here, now I have competition. This is exactly where N gamma occurs. Competition between the neutron being emitted or a gamma decay occurring. And that's where you see the characteristic exponential fall off over the first MeV or 2 before it goes away. Okay. So in the reaction, we're doing yttrium 89 PD, right? Now we also do PT. I mean, these other reactions just don't turn off, to help you with your experiment. So you also have PP prime. So by using the silicon detectors, you can. The reason that we use the silicon is so you can separate the protons, deuterons, and tritons. They preferentially lose energy at different rates in the silicon, so you can separate them out. So we can gate on the deuterons, which is right here, and then just look at those spectra, okay? So there's something like 100 million events for the PD in several days. So then here you go. This is the projection of all the deuterons, so now you're in the yttrium 88 nucleus right here, okay? Then you've got the ground state, next excited state, et cetera, and then you start to get to a high enough level density, right? There's just so many states there, it looks like a continuum, right? There's no single guy standing out as a big signal. Then as you get up to SN, right, now this is the region where you could be in the yttrium 87 nucleus or the yttrium 88 nucleus, depending on how quickly that neutron decides to leave, right, and goes up. So this is the denominator for my probability, right? I need a very clean spectrum here in order to understand what's going on. The contaminant is carbon and oxygen, right? Target's oxidized. Nothing's pure. I don't care what the company says. Check it. Then, in coincidence with that, we're measuring these gamma rays. So this is a gamma ray energy going up here from 0 to an MeV. Okay, that's 100 keV, 1,000 keV. And then, again, this is the ground state. It's almost the same plot, okay? Now we're looking at the gammas. There should be no gamma rays with the ground state. That's good. And then as you move up, you'll see different states turn on, right? And the gamma rays that they produce start showing up. That's great. And as you move along, you'll notice they persist. And then all of a sudden, magically, after they hit the neutron separation energy, they all drop off. And then new ones will show up. Well, because now I'm exciting states in the next nucleus, yttrium 87, right? So you can see this transition. I know these guys should decay all back down to the yttrium 88 nucleus because there's no other way for them to go. As soon as you cross the barrier, or the neutron separation barrier, boom, 2 different things happen. Some of these things have fooled us because they persist for a long time, and there's new physics in there. They're bringing in a different spin than neutron capture would, and their spin-inhibited decay, which is a physics article on its own that you got to write up. So that's the numerator up here. So then I get my gamma ray probabilities. The spin issue we looked at, so this is now an excitation energy. So right below SN, here, we have a pretty broad distribution of spins, and it's not 0 and 1 and 2. That's where the neutron capture would kind of cluster, mostly in 0 and 1. Depends on the nucleus you're hitting, of course, because it could have a high spin as a ground state. But then in between, you'll see that at SN, things drop off, but not everything drops off. Well, that's because there's a bunch of states in there that have a higher spin, and in the next nucleus they got to go to, when the neutron evaporates, there's no spins that overlap. So they can't decay. Then you go a little further, and then other states open up in the yttrium 87, and all of a sudden, boom, these guys shoot up. This is Zirc 90, but it happens the same in yttrium. And then you'll see that the distribution of spins over here changes. We're finally starting to get into the details of being empirical, through the experiments, pull apart the spin distribution and angular momentum problem. This has been at the core of N-gamma reactions for quite some time, for surrogates.
I don't understand why you would have spin 0 and then a half there.
Zirc is not spin. There's a spin half in the ground state. Or
Yeah.
sorry.
Yeah.
If that's spin 0, then I got one of these guys adds up to a half, and then
Yeah.
3 halves, and
No,
then to a half.
the two blue dots right on spin 0 are offensive.
He's probably a plotting issue.
Okay.
Don't worry about that.
Right.
He's also 0, so
Yeah.
that's very suspect to me. Right. Same thing here, right? Same
Yeah.
thing there. Yeah. Root can sometimes get you. So. But anyway, for years we've thought about different ways of looking at it, but we finally had enough statistics to be able to break things down a little bit and examine where everything went. Anyway, that's helping our theorists and also giving them conniptions, because now we can check them a little bit, and so it's all going to be positive in the end, but there's a process to understanding physics. So at the end of the day, I generate gamma ray probabilities. So we gate on a certain gamma ray, okay, that's in the cascade for the yttrium 87 nucleus, for instance, or the yttrium 88, because that's what you're capturing to. And we see at SN it drops off. Then same thing over here. This is the 232 gamma ray. It's another guy. There's some structure where there's discrete states being fed. Then you get into a relative continuum, and then it drops off. Same things here in 983, and then wait, what's going on? It came back up. Mother Nature's never nice. In the next nucleus, there's a 982 gamma ray, of course. So you've got to be aware of these things. 299, same thing. You get to SN, and you drop off. And then the 142 guy, you drop off. So I don't want to speak too much, but theorists basically then take the gamma ray probabilities, they work on the gamma strength functions, and they work out the optical model potentials, etc. They take into account our probabilities, and then we can generate cross-sections. That sounds easy. It's not. But at the end of the day, we've basically been able to measure, this is the ground state to ground state cross-section here, and this is the isomer to ground state cross-section on the far side, okay? Previously, where is it? The red line has been what the theorists at the lab were saying was it. And then magically, when you have a measurement show up, all of a sudden their error bars triple or quadruple in size, and then we agree again somehow. And to be honest, they did their level best with the information they did have in hand to try to predict these cross sections, but we're finding they could be off anywhere by a factor of 2 or so in situations. Similarly, for the ground state to the isomer and isomer to isomer, the blue line was what we had before. The black line is what we have now, and that's a couple of factors there. Same thing over here. And again, these error bars all of a sudden appeared just as our data came out. So there's not really there's definitely there's an external force acting on the modeling people. And then likewise, this was what they had in the codes, for their evaluations and everything. And then this is what we're measuring similarly here. So it isn't a direct neutron measurement of what you care about. It's an indirect method. However, it sure as heck adds some guidance and some data to help you support your understanding of what's going on. If I could make these targets, I would. That's the way to do it, but you can't. So trying the next best thing. And this is just a summary plot of the 3 different situations. Now, my enterprising postdocs and grad students have thought of different ways of using this information. So Richard Hughes is working on Hyperion as well. He said, well, wait a second, do we know everything there is to know about yttrium and zirconium? If there's more states there, that's good, because we can use this data to pull something out of it. So he said, okay, fine, I'm gonna just gate, just for the heck of it, I'm just gonna gate on an excitation energy here of about a few MeV, and I'm gonna see what kind of gamma rays are associated with it. And lo and behold, he finds 1, 2, 3, 4 new gamma transitions that haven't been absorbed before. And he's also found 1, 2 new states that go with it. And that was just in the first pass of things to take a look. So by having the ability to excite the nucleus to a specific energy and then stop there and look at the gamma ray cascade, you can really pull apart what's going on in the nucleus. And no one's really, taking advantage of that. It also helps that you have your own setup and you can play games with these things because we own it. We're not applying the time at like Gammasphere and then waiting a year and a half and then getting beam, etc. Nothing wrong with Gammasphere, it's just when we need to measure something, we need to do it quickly. Are we done with this? No. There's tons of other things to look at, including benchmarks, et cetera, et cetera. So we know that, we're working on these things, and that's an ongoing project. Another thing to do nuclear structure, and this is old school nuclear structure, is do gamma-gamma, so that you can connect two states together through their gamma transitions. And so when you get a coincident gamma ray in one detector, you can look for another one, and then you get these points. These characteristic points tell you that these guys are in coincidence, prompt coincidence with each other, and you can build stuff up. The problem is, our array isn't that efficient. We only have 6 clover detectors right now. So we're not nationally competitive at this point. So that makes that kind of thing pretty tough to do. So that brings me to Hyperion. So he's the god of light, Greek god of light. He's one of the titans, actually. So that's an upgrade, or it's working right now as an upgrade to our Starlighter system. So instead of the 6 clovers, we want to have a bunch more. So back in, it says here, March 2013, I said, hey, we're really suffering for statistics, right? This is around the time we're going to do these experiments. And then, so that's me, nominally. That's a 6-foot high, representation of something. And then Scott Fisher, who's a really good designer over the lab, like mechanical, electrical designer, he threw in a bunch of clovers, and I said, well, we want more, right? How much more can we stack in there without hitting anything? So then he threw in more. So this is 16 clovers, because there's one on the bottom, one on the top, that we had to lose. We showed this, I made a 3D printed model of this, and I showed it to some of the guys from Washington when they happened to be coming by. And literally, I knew they were coming on Thursday, and I had it printed over the weekend kind of thing, getting ready for them. And then they gave me a bunch of money to make the frame, because they said, hey, this looks great, I want to make this happen. So we got a bunch of money, literally I was in the office and phone rings, I pick it up, hey, you've got a couple $100,000 sitting in your account, by the way, build this frame, get going. Okay, next day the account's open, you get going. So we didn't have enough money to buy the detectors. Because a couple $100,000 doesn't go very far, right? So, it turns out each one of these is almost $200,000. So I'm like, okay, I'll do the next best thing. I'll build the frame to hold 14 clovers and all the electronics and support, cabling and all that jazz to go with it. And then I know there are clovers or the former clovers from Yale, they're called in CloverShare now, and then there's some clovers at Oak Ridge that our colleagues work with. They don't work at them all the time. Maybe we can collaborate and we'll borrow and, et cetera. So we went from effectively 5 positions, because we had a flaky one, to 14, which means we go from 3 times for gamma singles alone, we'll go 3 times up in the capability. And for gamma-gamma, it'll be 8 to 9 times, because you get the efficiency squared amount. So then we moved on to a little better design. We looked at all the different angles we might want to include to make sure we weren't going to miss anything important. And then here's the gamma-gamma efficiency. So my estimate based on the current efficiency, we're going to be up over 10%. This is half of Gammasphere's efficiency. So for people who don't get Gammasphere computers, now we're getting competitive. Because gamma-gamma is squared. Okay, this is the final design. I love 80-20. I don't know if anybody's worked with it. Of course you guys have worked with it, but that stuff's great. So instead of trying to weld all this, we made it all at 80-20 so that we can add on and take off things, etc. So of course you got to have the logo on here. So what happens here is this wheels the $1 million or so worth of clovers in and out, so you can get around this chamber, because this detector is going to smack you if you try to move out of the way. and then down the rail, because we don't have a lot of room on the sides over at Texas. So all of this stuff is real, I'll prove that. So we ordered all the material. This is the chamber, and this is the plates that go on to make the outer bits of it. So the postdoc Richard is very refreshing. He's like, "What's that?" He's British. I said, "Well, that's our chamber." He's like, "That's a block of aluminium, right?" And I said, "No. We don't just grow these things. You have to machine everything from get-go." So it was a very big learning experience for all these guys to see it come in as slabs, right? Then the 80-20 showed up. We built up the stands. I actually do work. Then we finished it. So this is like a couple weeks ago. So here's the chamber in the middle, right? Here's the array. We have one BGO shield in just to make sure everything fit. It fit. It was good. You never know until you try it. And so that's Perry from here. Shia Ota from Japan. Richard's my postdoc. He's from England originally. This travels about 12 feet, roughly, front to back. And then this is showing it closed. So here it's open, here it's closed. And you're looking right at the target chamber right in the middle there. So this entire thing will ship off, and all the electronics and everything we already have, to Texas. We'll load it with we'll remove our old system, put in this one, and then we'll have the capability for 14 clovers in a much better efficiency. Okay. Next one, this is for N2N research. So that N-gamma one is for nuclear structure, Hyperion's for nuclear structure and N-gamma measurements. Neutron Stars. At the lab, we have something called LDRD, Laboratory Directed Research and Development Fund. I put in a proposal to do neutron measurements, like from NF, and then get neutrons out from fission, as well as N2N measurements, and I didn't even think about it, but we can also do NN prime. Of course, that got turned down. But no good idea completely dies, right? So you keep it around. And then when we got proposals in for NE22, we're like, well, look, we think we have a better way to do this. We're going to try it. So we want to develop a large scintillation array to moderate and directly detect the neutrons. Now, large scintillation array could be anything, right? So solve long-standing measurement issues related to neutron multiplicity as a function of energy. So we want to measure the neutron multiplicity as we excite the nucleus up in fissions, right, for the actinides. I didn't say we're going to get the neutron spectrum. That would be cool, but a scintillator like this, where we moderate, won't do that. So the idea here is we want to perform model-independent, or as independent as you can, measurements of N2N and its byproduct N prime. So currently, people will take a neutron beam, hit a target, like at Lance, okay, or around the world, and then they'll look at the gamma ray cascade feeding down to the nucleus they care about. There's a lot of modeling and theoretical guesswork and or estimation in understanding what that gamma ray cascade is. If you detect the two neutrons, you don't care, right? You just, not that I don't like my theory friends, but you don't need them to interpret that. So I saw the opportunity to not develop this and just use what's at Texas. It's called neutron ball, if you just consider the outside part. And then we got money from NE22, et cetera. So the challenge would be to measure the efficiency and develop the ability to measure the continuous events from neutron ball. It's a slow detector, and I'll show that in a second. So the inner cylinder is divided into 4 segments. There's 1, 2, 3, and then on the other side 4. So 4 big pie slices. 2 end caps. This is in meters. So this sucker is basically from here to the wall, big, huge, round cylinder. Neutron detection is by measuring the gamma rays from capture on natural gadolinium. So you get gammas between 6 to 8 MeV, depending on which isotope it captures on. And the array has been modeled in efficiency, but it's about 60% efficient for a single neutron capture. Not for any multiplicity, but just a single neutron, which is huge. So currently, we're going to be measuring end-to-end cross-sections on PU-241, 239, 233, and NEP-237. My French colleagues are working on U-233, so if they can do that, then I don't have to. But that's one of the ones on the books. There are very little end-to-end cross-section data available on the actinides. Sometimes making the targets on these unstable guys is pretty hard to do. Neutron backgrounds from fission are huge, and if they use a neutron beam to do it, you have the neutron beam-related backgrounds. That can be a massive problem. So, several people have tried this. I mean, Frejo and a few others have tried this in the 60s. And they had some success, but they always had this issue of the neutron beam itself inducing a large background in the room. So N2N on plutonium's here. There's huge gaps in the neptunium, and there's just no data over here. So this will be the first time we try to do this will be plutonium-241. There's a choice for that. We can't do any worse than this, right? If you just don't have data, you're going to make an improvement. 241 has a 14-year half-life, so we're not making a target of that. We're making it at a PU-242. That's 375,000 years, no problem, we got that. And we're going to get the neutron, we're measuring this from 0 to 20 MeV. We already have 99.96% pure stuff. That's a good thing about being at the lab. They have really nice stockpiles of small amounts of materials from ancient times, 50, 60 years ago, etc.
Is there any chance of getting better resolution at the lower energies on 239?
Well, we're
That
going to get
data
about,
you saw is like every 5 MeV or so.
yeah. No, we're talking 100 keV bits.
Oh, yeah.
I'll show you that. Yeah. So this is going to sit here. This is still at Texas A&M, right? This is where Hyperion is going to be. This is where Starlighter is. And then right beside that, there's this big neutron ball. So we're calling Neutron Stars because that's way cooler than Nimrod. Sorry. So it's 3.5 tons of 0.3% gadolinium doped into pseudocumin. That's what that is. And then it is thermal neutron detection. Okay, so the neutrons come out, they moderate, they capture, then you get the flash of light. The phototubes see that. There's 20 of them around there. Okay, but it is slow, so you can only run at about 200 to 300 hertz or so. There are gamma backgrounds that can cause false detection of neutrons, for sure, right? So you've got thallium-208 line from your thorium decay chains, etc. You got your potassium-40. So you can't put your threshold down at like 100 keV, like you would like to get everything. You're probably going to have to put it up here around 2.5 to 3 MeV to get above this line. It depends on what we see when we start turning it on again and looking. But basically, we're going to have to know the efficiency because we're going to have to make a cut here, take everything above that, and call that a neutron capture, okay? Or a neutron being observed. So with the 2.8 MeV threshold, we see that we've got about a 55 to 60%-ish range here for the efficiency. This is less than 500 microseconds, meaning anything longer than that, we're not going to count because you're going to get into the next event. Okay? And we see that what Robert did was threw in 10,000 neutrons. There's a moderation time as you come up here, and then there's a capture time as they find gadolinium in the material. So we're going to be setting a window of about 100 microseconds to count that as a prompt event. Okay? All right, 2 quick movies. This is always fun doing this backwards here. Okay. What we're worried about a little bit is after they moderate, thermal neutrons can travel around and just kind of hang out in the detector and add to our background. So on the left is with no absorbing material. And this is going to run to about 400 nanoseconds up here. So what he's done, the green is gammas and the purple dots are the neutrons. So you can see we're at 250, 300 microseconds, and that's 416 microseconds. We've got a bunch of neutrons kind of hanging out that haven't really captured. They're in the gaps here of the chamber. If we bring the gaps in, we're going to gain about 20%. If we could lower our gamma ray threshold, we gain about another 20%. So for first order, we're just going to run with it the way it is. But we would like to add some kind of neutron absorbing high capture material. So if we put gadolinium around, you see them rattling around, but then at already 200, that's 300, that's 400. There's only like a couple left, right? So we don't want our fission-induced neutron background, because that's we're going to get a lot of neutrons from that for the active ions, to give us a target-induced background we can't get rid of, okay? So we're thinking about adding something in to absorb. So anybody got ideas on that? All layers of it. This is what the chamber looks like. That's going to go inside of the neutron ball. So this technically is this is the stars part of it. So it's a silicon telescope array for reaction studies. So the beam comes in from the right to the left. We scatter off the target and go into our silicon telescopes. We know what we excite the nucleus to, and we can observe the neutrons flying through the chamber and out into the sphere around it. Here, these detectors are going to be used to actually tag on fission, so that we know if there was a fission event or not a fission event. We also know that there's about 10 gamma rays liberated per fission event, so we're going to see a gamma flash associated with every fission in the sphere. So we'll be able to confirm that because we'll see the neutrons from it and the gamma flash from it. So this is going to be kind of neat to pull this all apart. The signals are read out through these breakout boards, which then punch through the vacuum chamber wall. This is kind of neat. We stole this from Texas. I'm Steve Jobs, nuclear physics. I'll take any good idea from wherever. My postdoc over there had come up with a way to kind of mount some circuit boards right through the vacuum chamber. We kind of did a little improvement on it, but essentially the outer layers of the boards are ground planes, so they're dead smooth. Okay, and then we put them through a slot in the aluminum, and on the other side we have a little bucket, and we fill that with Torseal. And then we let it sit properly and clean it up, bake it out, and make sure it's all dry. And we pumped on it, no leaks. It was great. We get 32 channels through here for like $10 a board, not even, super cheap. And we make it in our lab, any length you need, configuration, whatever. Okay. So to be a little more pedantic about it, so when two neutrons are detected, it's not necessarily end-to-end, right? Because each possible reaction will have a distribution of detected neutrons. So N prime is 1, N2N is 2, N3N is 3, fission is several, and it changes, it's not always the same. So with no neutron background, the neutron detection probability is simple binomial. You have 1 neutron generated, 1 detected, it's a 60% probability. But if you imagine you have a background of neutrons, right, that are coming from the room, then everything kind of shifts to the right a little bit. So we have to be a little careful in how we unfold the analysis at the end of the day. That's all we're pointing out. It's not just straight, like I saw 2 neutrons, I'm good. That's not good enough. So we did a bunch of modeling. I had my summer students work on it, and then Robert worked on it again, and I double-checked everything that came out. But what we did was we took the PU-241 evaluated data, because there is no actual measurement yet. So NF is the green line, like first chance, second, third chance fission. NN prime rockets down here, N2N turns on at the threshold, and then 3N turns on later. The raw neutron spectrum, just adding up how many neutrons you'd see, either 0, 1, 2, 3, etc., are shown here. Then what we did was we run it through, okay, we know what the model looks like for the efficiency, let's run it through and just count real statistics and see what kind of, answer we get at the end of the day. So we get about an 8% uncertainty for, this is 100 keV bins, right? 8% uncertainty all the way along for N2N. Less than that for NN prime, it's bigger cross section, higher problem, get more counts. And then a little bit worse for N3N, of course. Okay. And then if the neat part is if you're wrong, somehow you've done your efficiencies wrong, your N2N cross section goes negative. And then below here, because remember this is neutron energy, below here where we know the nucleus can emit a neutron, right? We should see nothing. So we have built into this a few different ways to check things. Below here, there should be no neutrons in coincidence, that would be background. If you overcorrect or get your efficiency wrong, your N2N stuff's not going to look right at all, where it shouldn't be, right? And then for fission, you're going to have that going along as well. That's in the model, but not shown. So it's always good to measure enough things to cross-check yourself on every measure. So we've already Monte Carlo'd this, designed the chamber. We wrote a little report on that. We've got the data acquisition being updated. We've got target fab underway. The chamber's out for fabrication actually right now. Coming up, we're going to be testing and installing that chamber. Then we're going to write a little report on it because you want to write like a little NIM article or something on it. And then we're expecting to field our first experiment around April. That's dependent on beam time, so that gets left. So this is just a little summary of what's going on. Okay, Hydra. This is the last one. This will be quick. So my grad student, John Coughlin's looking at this. He's from Penn State, actually. And he's working on a fellowship. So a few years ago, I wanted to look in more detail at low energy fission because the surrogate regime kind of broke down when you had discrete states right at the fission barrier. We wanted to understand that better. And this is the same thing that Chip Britt and friends pointed out back in the 60s. They actually tried to assign the spin states, like the K states, etc., to the fission system. So when John was working for me as an undergrad during the summer, we investigated different ways to detect fission that was cheap, like inexpensive. And we found out that there were solar cells from the 80s that didn't have any anti-reflection coating on them. And they worked really, really well, surprisingly. We got some nice ones that had the AR coating. They were great as battery, light sensors, but not as fission detectors. They ranged out fission fragments. So this is data, okay? This is counts into one of these little solar cells, fission detectors we call them. And this is your heavy and light fragment from California. He ran that for like 3 or 4 days kind of thing, just get a clean spectrum as he could to prove that it worked. And then I think he won the summer student poster symposium thing because of this as well. Then we set this up and we did a quick run up at Berkeley a couple of years ago just to prove that we could do coincidence measurements. So here are the silicon telescopes. There's a delta E here and then a thick delta E detector in the back. The E detector is 5 millimeters thick. It's one of the thickest and biggest area ones that Vortec ever made. So the array of these things is about 14 or 15 of them. It's about 50 grand or so. It's not cheap. These are $2 each, so I was really happy with that. And then they're all wired out, and you can't have light on them because they do respond to light. So everything's dark during the actual experiment. And then there's a target ladder here that runs up and down. Here you can see we did DP. Okay, so it's deuteron beam, 20 MeV. Looking at the protons out. Protons are here. Okay, here's the deuterons. And we can see discrete states being populated and then kind of a continuum. Okay? And we have a lot of streaking. We didn't fully deplete the silicon detectors, the thick ones, because we biased them to what the company told us they would do. Be fully depleted at. Totally wrong. So we're going to do a test experiment or two. We just take some beam and then try different voltages and make sure everything is completely working right, and then we'll do our experiment. So what we're doing here is we got fission in coincidence with the excitation of the nucleus, and then on this side you can see we're looking at, this is the probability of fission, and you can see there's little bumps and wiggles along the way here. These are different states being excited and fissioning in the nucleus. This is 240 is the compounds. Plutonium-240 is the compound nucleus going away. And then we get up a little bit higher, and then we start having trouble because the Coulomb barrier stuff kicks in, and we don't see it. But we took a look and saw how well this matched, and this matched really closely with what Chip Britt and Jerry Roney and a few other guys have been doing back in the day. And you can look, a lot of this stuff's in Huizinga's book on fission. You look in there for charged particle-induced fission. So in order to get that, these are just on an aluminum plate with some Teflon and tape, but it worked. Okay, it's proof of principle, right? Now we're making something called the Death Star. I'm sticking with Hydra, but the guys like to call it the Death Star. You'll see in a second why. So this is a sphere that we can buy for $400. It's real thin steel, but very spherical. We know the angles really well once we machine all these holes in it. So we're machining all these holes. So the silicon telescope is going to sit in this slot here, and these guys are going to be all different solar cells for detecting fission, because we want to measure the fission anisotropy, the distribution of the fission fragments following the induced fission. Okay. So then we put it on a plate, of course, because we need to put it in vacuum. Beam will go through this hole, through the hole in the back, and then this plate will be aligned with the beam line up at the 88-inch. We're doing this at Berkeley in K4C, where the beam quality is pretty good. And then you populate it with all the solar cells. So John and I and a designer at the lab for circuits built up all these little solar cell things. They're little plug-and-play units, so we can solder up all the connections out to the back and leave them in place. And then on the inside, I don't want to be the guy doing this, but on the inside, you just go and you plug in your solar cells all over. Right? So of course we have the summer students make like 100 and something of these this summer, right? And then not the grad students, summer students. Just be careful how I say that. And then test a bunch of them to make sure they will work. So if something goes south, you just pop out one little detector and put a new one in, because they will be contaminated, right, at some point once they get exposed. And then around the outside, you've got all your silicon telescopes, and the idea here is that all these different angles that we cover, from about 10-ish to 90 degrees, and then 90 to about 170 or 60 degrees, we're going to be able to vary the spin we bring to the system by varying the angle, and then hopefully see different anisotropies. And John's done a bunch of studying on that to with the theory and the data that has been published to see how well we can do on that. And it's pretty encouraging, actually. Okay, and then, of course, you got to put it in a vacuum chamber at the end of the day. So the beam will go in through there. And this will sit at Berkeley so we can come back and do different testing, et cetera. All right, so at the end of the day, with all the people involved, there's the Livermore folks, Robert, Richard, Nick, Shuya, James Benson, he's a physics scientist, almost has his PhD based on the zirconia beam. John from Penn State, Tony is joining us, Justin, who's wrapping up. On the theory side, we have Yuta Escher, Ian Thompson, Eric Ormond, Gregorio Patel, who's actually from Jolie Jachevsky's group, but at Livermore. In RadCam, couldn't do this without these guys, Roger Henderson, Kevin and Kip, Don and Eve. They are all integral because they have the actinide labs. We can actually go and make all these different samples and do the chemistries and clean the samples, et cetera. And then at the end of the day, the guys that get the data are Brett and Caleb. At Texas A&M, there's a whole host of people, but the main players are Ellen, Bob, Sherry, and Chris. Then broader people that collaborate with us are from Richmond and all over the place. And then just a summary here to show you around the world. It's Berkeley, Berkeley National Labs, where we were, Flannel, Texas, Oak Ridge, Ohio, Richmond, Rutgers, St. Mary's up in Canada, Surrey in England, AWE in England, CA DAM, B3, that's like Rio Lachatel, like Livermore in France. Bordeaux is their, like their Berkeley lab. And then JEA Tokai, that's where she is from actually. And then Livermore. So, any questions? Thanks very much.
I was wondering if you were interested in combining the techniques with the fission product detection as anti-coincidence to measure those end-to-end cross-sections.
So, oh yeah, absolutely.
That's
No, we have, the reason we have to have a high efficiency fission detector there is to veto the neutrons.
exactly.
Yes.
Okay.
Yeah, that's like 40% solid or something, to be able to do that.
Other questions?
I explained it so well.
Yeah. Any ideas how to, you can go ahead.
I was just wondering why yttrium?
Yttrium is a RadChem diagnostic. So at the lab, people use it and they want to understand this cross-section. There's a whole bunch of them, but nobody had a way to measure the cross-section. So this has been a problem for 50 years. And we're actually solving it, so that's good.
Any suggestion for neutron spectroscopy at kiloelectron volts without line of light?
So yeah, I don't know. So we looked into being able to do do an NP reaction of plastic, to use that instead. And
Inelastic,
Yeah.
Alamos, whatever.
right, so for neutron stuff, we found that it had to be a few hundred keV before we could see enough electrons to be able to say statistically relevant, and really pin the energy. Because we were thinking of using a big plastic detector around that. But it turned out it needed to be at least 500 keV neutrons or more. And when you do end-to-end and you're just turning on, those neutrons are going to be very low. So we'd have a big gap at each, spot. So we decided to go with the thermal capture instead. We did look at it though. We ran some simulations.
Any other questions? Okay.
Do you have connections at all with like the nuclear safeguards world?
No.
People who are doing like delayed gamma spectroscopy and
That's Nick Scelzo in our group actually.
who?
Nick Scelzo, SCIELZO. He's given a talk here before. But yeah, he's doing it to try to understand stuff really far from stability. He's not doing it to detect anything. So he's doing atom trapping at Caribou up in Argonne, where they have a big fission source, and they'll trap radioactive species and then look at the beta recoil and neutron correlations. In fact, I can tell you all about it. She's doing it for her PhD. So I defer. It's called passing the buck. You'll learn how to do it with your PhD. Oh, the other thing is once you get your doctorate, you no longer do things by trial and error. It's successive approximation. You can write that down.
Okay, so thank you very much. Before you leave, come ask me to announce upcoming colloquia. So March 2nd,